Okay. So what we do today would be partly in the manner of a summary of what we have already learned. Okay, so we'll also tie up some loose ends that we have left out. Right? So by the end of this class, the idea is that you get a very basic idea of what quantum mechanics actually is, right? The basic mathematical framework of quantum mechanics. Now, once you have followed all these courses, I believe you have got an idea about what do you say, the complete picture of quantum mechanics, and the rest are mathematical details. All right, I have given you the logical framework, I have given you the mathematical framework. Okay, and if you familiarize with these things, the rest are mathematical details. All right, there are certain things that you might have to learn, including some mathematical tricks or some mathematical theorems, but this is the basic framework of quantum mechanics. So first we'll discuss the postulates of quantum mechanics. Okay, so as I said, the postulates of quantum mechanics, we have already seen these things. I am just putting it in a formal manner. All right, and it's also basically a summary, essentially a summary of what we have been trying to communicate during these past days. All right, and we'll also discuss an interesting thought experiment called the Schrodinger's cat. It's been quite notorious. It has been quite a notorious cat, this Schrodinger's cat. And then we'll, if time permits, we'll go into the interpretation problem. So these are the postulates of quantum mechanics. So we start like this. There are observables. All right. So we motivated these postulates in a semi-logical manner using the double slit experiment. All right. Now we have reached the point where we can just state the postulates and construct the theory from there. All right. So these are the postulates. There are reasons why we take these postulates, etc. There are motivations. I have already given them. The motivations are experimental. Okay. So the first postulate is regarding the observables. Observables means measurable quantities. Okay. And the postulates of quantum mechanics, again, you may not get the same set of postulates when you take all textbooks. All right. There are different formulations of quantum mechanics. Okay. What we have been discussing is known as the Hilbert space formalism of quantum mechanics. Right. The Hilbert space formalism of quantum mechanics. Now, even the Hilbert space formalism of quantum mechanics, it doesn't have really this specified set of postulates in exactly the same manner. Right. Different books express it in different manners, in different ways. There are other formalisms of quantum mechanics, interesting formalisms of quantum mechanics, which are equivalent to this in the terms of predictions and the terms of the basic idea, etc. All right. Most interestingly, there is this Feynman's path integral approach, the path integral approach. Right. So these things are interesting, but we are now talking about the Hilbert space formalism. Okay. All right. So it has the following postulates. The first postulate is regarding the observables. Right. So corresponding to every observable quantity like energy, momentum, etc., there exists a Hermitian operator. There exists a Hermitian operator. Right. I told you why we chose Hermitian operators. Hermitian operators have some nice properties. Importantly, their eigenvalues are always real. Okay. And even more importantly, the eigenvectors form an orthonormal set, which is fundamental to quantum mechanics. The measurable values of a physical observable are the eigenvalues of the corresponding operator. Okay. So we have a Hilbert space for every quantum mechanical system, and every observable quantity is associated with a Hermitian operator, and measurable quantities are eigenvalues of the corresponding operator. Okay. And the second postulate is regarding the state of the system. Okay. To every physical system, there corresponds an abstract Hilbert space. Okay. A state of the system is represented by a vector in this space. Alright. The states are represented by vectors in Hilbert space, and as I said earlier, Hilbert space is called the state space. It's a name for the state space or the space of states in quantum mechanics. Right. So not only is every state represented by a vector in Hilbert space, but any vector in the Hilbert space represents a possible state of the system. All right. So corresponding to every system, the correspondence is 1 to 1. Corresponding to every system, you have got a vector in the Hilbert space, okay? And every vector in the Hilbert space is a possible state of the system. Okay. All right. And by taking this postulates, there are two. There is this important property of superposition being incorporated into quantum mechanics. That is, if psi1 and psi2 are possible states of the system, okay, if psi1 or psi2 are possible states of the system, then so is this, right? Because if psi1 and psi2 are possible states of the system, it means that corresponding to they correspond to some physical state, but any vector in the Hilbert space also corresponds to a possible state, right? That's part of the postulate. Any vector in the space also represent a possible state. Now we know that once we have psi1 and psi2, any combination of this form is also a vector in the same space, right? That's known as the property of closure. So we have got principle of superposition. And the way we motivated principle of superposition was by observing the double slit experiment and choosing a specific interpretation that I will talk about in the later slides. Okay, and we said that particle actually exists, the electron actually exists at two places at the same time. So we need some kind of a superposition thing. And here, this is the way we incorporate superposition into the mathematical framework of quantum mechanics. Okay, and another important part, you can consider it as a corollary or as a subsection of this postulate. A state vector can be expanded in a complete set of basis vectors, right? You can expand it like this. And the important part here is that in quantum mechanics, the basis vectors that we use in quantum mechanics, the basis, what are the bases? The bases are always eigenvectors of observables, almost always, all right? We don't have to use anything else. Okay, so always these are eigenvectors of observables. This is why we are interested in Hermitian operators. Observables are Hermitian operators. Okay. And the third postulate is regarding measurement. Okay, the third postulate is regarding measurement. We need all these postulates. Okay, so if we measure the value of an observable represented by an operator, a Hermitian operator, the outcome is one of the possible eigenvalues of this operator. Alright, so that's the postulate regarding measurement. If you measure the value of an observable, a physical quantity, the outcome is one of the possible eigenvalues of that operator. Okay, if the state is represented by an eigenvector of A, right, it's possible that the state, because any vector in Hilbert space is a possible state of a system. Alright, so if the state given is a if the state given is a eigenvector of this operator, okay, is an eigenvector of the operator, then the measurement of A will give the eigenvalue corresponding to that eigenvector. Alright, so the measurement of A will return the value, this eigenvalue. Okay, is that clear? If the state is an eigenvector of the observable that you want to measure, alright, then you get the corresponding eigenvalue when you make the measurement. There is no problem here. These are known as determinate states. Right? Eigenvectors are states with definite values of an observable. Right? So if it is in an eigenvector, right, if the quantum mechanical system is in an eigenstate of an operator, these are determinate state. Right? So which means that if the state is in an eigenvector or eigenstate of operator A cap, whenever you measure this observable, you are guaranteed to get the corresponding eigenvalue. Right? So these are states with definite values for this observable. Alright, these are states with definite values for this observable. Right, these are called determinate states. These are called determinate state. Okay, determinate state because they are well defined. Okay, now so there is no problem of probabilities here. If it's an eigenstate, you are measuring the corresponding operator, you always get this value. Okay. Alright, so eigenvectors are states with, and specifically you might have heard of stationary states. You might have heard of stationary states. Stationary states are actually eigenvectors of the Hamiltonian. Stationary states are eigenvectors of the Hamiltonian, okay, which are definite energy states. We have said that Hamiltonian is the name for the observable corresponding to, okay, Hamiltonian is the name of the observable corresponding to energy, okay, or the operator corresponding to energy, okay, and the corresponding eigenvectors are called stationary states. You might be familiar with this term. Okay. And part of the measurement postulate is also something called the state after measurement. What happened to the system when you make a measurement? I mean, these kinds of postulates we did not need in classical mechanics because we could always make measurements without worrying about what happens to the system. Alright, so this is an important part of quantum mechanics. On making the measurement of A on the system psi, okay, the system changes from psi. right? It changes from psi to one of the eigenstates of A. It changes from psi to one of the eigenvectors of A. All right. So which eigenvector? Eigenvector corresponding to the measured eigenvalue. All right. So suppose you make a measurement of an observable A cap, all right, on the state psi. Measurement of A cap on the state psi. After measurement, suppose you got the value an. Right? Suppose you got the value an. Then after measurement, this is the measured value. This means that after measurement, the state, what's the state? The state is the eigenvector of A corresponding to this eigenvalue. All right, that's what we can write it as phi n. Okay, we'll write it as phi n. That's what happens. So state of the system changes when you make a measurement. All right, and this fact is called as a measurement problem, or sometimes it is a problem. It's a measurement problem. We don't know how this happens. All right, we have to accept it as a postulate, because we saw that this happens in the double slit experiment. When you are not looking at it, it's passing through both the slits and you get the interference pattern. When you try to determine through which slit the electron actually passed, you always find it in one of the slits. All right. So initially, before measuring, it's in different states at the same time, and when you make a measurement, it reduces to one of the states. And this fact is often referred to as the wave function collapse. Right? It's referred to as the wave function collapse. Wave function collapse. Okay. All right. So when you hear the term wave function collapse, you know what it means. So where phi n is the eigenvector of A corresponding to the measured eigenvalue. Okay. All right. Now again, there's another postulate. You have to have all these postulates. All right. All these do not follow from a couple of postulates. We have a number of postulates here. Okay. So the thing is that you need a postulate regarding the probabilities of outcomes. Okay, because as I said again in the double slit experiment, we can experimentally measure the probability of measuring of observing an electron in one of the slits. Okay, all right. So this probability has to be predicted by quantum mechanics. All right. So this is the postulate that gives us the rule to calculate probabilities of measurement. If you measure an observable A cap on a particle in the normalized state psi. Okay, normalized state psi, you know what normalized means. Normalized means this. Okay, the inner product of that state vector with itself is equal to 1. That's what you mean by normalized. All right. In a particular basis, this means modulus of C1 square, or we can now write it in a short form, summation over I modulus of Ci square is equal to 1. We have seen both these things. You are certain to get one of the eigenvalues of the Hermitian operator. All right, it's not in an eigenstate of the operator; it's in some arbitrary state. And when you measure A cap, you will always get one of the eigenvalues of A. All right, and this is the postulate that says that the probability of getting the particular eigenvalue A n associated with the orthonormal state phi n is given by this. All right, so phi n here is an eigenvector of this operator A that you are measuring. It could be energy, momentum, anything. Okay, this is given by A n phi n. This is the eigenvalue, right? And what's the probability for measuring an eigenvalue A n? It is simply the projection of the given vector onto the corresponding eigenvector and modulus squared of it. All right, this is what we also wrote it as. We know that this is equal to Cn, modulus of Cn square, where Cn, what is Cn? Cn is the expansion coefficient when you expand the given state in terms of the eigenvectors, right? Eigenvectors of A. Okay, good. Now if the state is not normalized, of course you will have an extra normalization factor, but don't worry about it. You first normalize and then it is easy. Okay. If it is not normalized, you will have an extra normalization factor. Now there's one more thing regarding the probabilities of outcomes. It's known as expectation values. Expectation values, as we said, is synonymous. It is to be understood as the average value. Okay, and if these are the probabilities, then the average value is given in this manner. All right. If the state is normalized, of course, this is 1. If the state is not normalized, you also have this factor. Okay. So the expectation value is given by it's bra psi a psi divided by psi, all right, or bracket psi. Okay, so this is the average value. We actually saw this in the previous class. Now, so far what we discussed, the postulate that we discussed describes the system at a given time, at a particular time. All right. Now, what about time evolution? Right? The fifth postulate is regarding the time evolution of the physical system, of the quantum mechanical system, and the idea is that the time evolution is governed by the time dependent Schrodinger equation. It's given like that. Okay, by the time dependent Schrodinger equation. And now you could take this as the postulate. Okay, we need a postulate about time evolution. Right? It's okay to start with the Schrodinger equation as a postulate. There are different ways to do that. Okay? This is the thing that we like to introduce here. Okay? Or you can put some other postulate which is equivalent to this, which contains the same information. Okay. All right. So that's a summary of what we have discussed so far in the previous classes. So this is the mathematical framework of quantum mechanics. The rest are mathematical details, as I said. Okay. Now, all right. Okay, now we can do a problem. We'll see if we have understood all these postulates. Okay. So consider a system whose state is given in terms of an orthonormal set of three vectors, phi1, phi2 and phi3. Okay. So this is the state of the given system. All right. We already saw this state before. Okay. Now consider an ensemble of 810 identical systems, which means that you are preparing so many systems. You are preparing 810 systems in exactly the same state. All right. You are preparing, let's say, 810 systems exactly in the same state. Okay. In the state governed by this particular state vector, or this particular vector. Okay. Now each one of them in the state psi. If measurements are done on all of them, how many systems will be found in each of the states phi1, phi2 and phi3? Okay. This problem I took from one of the textbooks in quantum mechanics. Okay. Now the question is this: we know that the state of the system changes after the measurements. All right. So the question is this: so we know that the state of the system would change to phi1 if we measure the corresponding eigenvalue. It goes to phi2 if you measure the corresponding eigenvalue, and phi3. So some of the systems after measurement will be in the state phi1, some of the systems after measurement will be in the state phi2, and some of them would be in the state phi3. Okay. All right. So if you do this for 810 identical systems, how many would be left in phi1, how many would be left in phi2, and how many would be left in phi3? That's the question. Okay. Now that's an easy question. You can answer it easily. We first notice that the state is actually normalized. Right. So if you just take, you can do it in different ways. You take psi with psi. You see that we know that this is an orthonormal basis set. Okay, so just for the sake of completeness, I'll write it like this. We can write psi with psi like this. This is root 3 by 3. We need a star there, but these are real numbers, so there's no problem. And the ket phi1, okay, plus 2 by 3 ket phi2 plus root 2 by 3. Is it normalized? I think 3 plus 4. Yeah, this is normalized, all right. Root 2 by 3 multiplied by phi3, right? So this is this bra psi, okay, multiplied by, we have got psi root 3 by 3 phi1 plus 2 by 3 phi2 plus root 2 by 3 phi3. Okay. Now when you multiply, you have to combine. Okay, you have to combine each of this bra with one of each of these kets. All right. If you take phi1, you have to combine it phi1. You have to combine it with phi2. You also need to combine it with phi3. All right. I'm just giving you the way we do these things. All right. But you know that they have said that it's an orthonormal set. We can use that information. So we know that phi1 with phi1 is equal to 1. It's orthonormal. And phi1 with phi2, etc. is equal to 0. Okay. Orthonormal means they are mutually orthogonal. And the scalar inner product with itself is equal to 1. All right. So if you do this, you see that of all the combinations, only this one survives. Okay, phi1, the only combination that survives is phi1 with phi1, and it's equal to 1. Phi1 with phi2 is 0, phi1 with phi3 is 0, and phi2, again, it's the only surviving combination is phi2. Okay. Alright, so if you do this, you will see that also using the fact that phi 1 with phi 1 is 1, phi 2 with phi 2 is 1 and phi 3 with phi 3 is 1. What you get is, so you just multiply root 3 by 3 multiplied by root 3 by 3. So that would be what is it? So it would be 3 by 9 plus 4 by 9, okay, multiplying these two, okay, plus 2 by 9, okay, so that is 9 by 9 equal to 1. So you see that it is normalized. Now normally you may not have to do all these things, because we know that the once you choose an orthonormal basis, the expansion coefficients square gives the probability. You can simply add modulus of C1 square plus modulus of C2 square plus modulus of C3 square and see that it's equal to 1. Alright, you may have to do only that. Alright. Now what we need to find is that once this is normalized, then the modulus square of this is the probability that the state will reduce to phi 1 after measurement. Alright, the modulus square of this is the probability that the state will reduce to phi 2 after measurement. Right, the modulus square of this quantity is the probability that the state will reduce to phi 3 after measurement. Right. So what is probability? By probability we know that the probability that the state will be in phi 1, for example. Alright. This would be the number of systems divided by the total number of systems which end up in phi 1. Am I right? So that's a fraction. That's the fraction. So the probability is actually a fraction of the total number of systems. The probability is actually a fraction. So if you multiply it by the total number of systems, you will get actually the number of systems which actually ended up in that particular state. Okay, that's what we do here. So N1 is the number of systems which end up in the state phi 1. Okay, that's 8, 10 multiplied by P1. 8, 10 multiplied by P1. So P1, alright, P1, the probability 1 is actually, you see from here, modulus square, modulus C1 square, that's equal to 3 by 9 and that's equal to 1 by 3. Is that correct? Yes. Okay, so that's the probability we have got. So that is 270. So we know that after the measurement, 270 of the states will be in the state phi 1. Alright, or 270 of the systems will be in the state phi 1. Right. Similarly, you do the same thing for this. Here the probability is 4 by 9, here the probability is 2 by 9. So 360 of the systems will be in the state phi 2 after measurement, and 180 systems after measurement will have changed the state from psi to phi 3. Okay, I hope that is clear. We could do one more problem. So here is a system which is initially in the state. Alright, these problems I chose specifically to get familiar with the postulates that we discussed so far. Right. So a system is initially in the state root 2 phi 1 plus root 3 phi 2 phi 3 phi 4 divided by root 7. Right. First we check whether it's normalized. Whenever the state the system is given, we check whether it is normalized. Okay. When the state is given, we check whether it is normalized. So you see that it's equal to, you just add modulus of C1 square plus modulus of C2 square, etc. Right. So that would be 2 plus 3 plus 1 plus 1, right, divided by, there's a square root of 7 here, divided by 7, that's equal to 1. Am I right? Yes. Okay, 1. So this is normalized. Okay. This is normalized. It makes easier, makes life easier. Now, phi n are eigenstates of the system's Hamiltonian such that, so this is the eigenvalue equation, right? These are the eigenvalues of the Hamiltonian. H cap phi n equal to n square epsilon 0 phi n. Okay. Now the question comes, now the first part of the question is, if energy is measured, what values will be obtained and with what probabilities, right? What energy values will be obtained and with what probabilities. So it's already given that these are eigenvectors of the Hamiltonian, okay? And we know that the measured values are eigenvalues. Right? So the rule to calculate the eigenvalue is given here. It's n square epsilon 0. Epsilon 0 has dimensions of energy, and n here is 1, n here is 2, 3, 4, etc. Right? So the possible values of energy would be 1 square epsilon 0, okay, 2 square epsilon 0, which is 4 epsilon 0, all right, 3 square epsilon 0, which would be 9 epsilon 0, and 16 epsilon 0. Okay, these are the eigenvalues, right, corresponding to the eigenvectors, and these are the values that you expect when you make a measurement. You will get one of these values as the energy measurement. All right. What are the probabilities? What's the probability of getting epsilon 0, energy epsilon 0? You take the expansion coefficient of the corresponding eigenvector and take the modulus square of it. That would be the probability. That's our postulate. Right? Or you could alternatively find it by looking at epsilon 0. What's the eigenvector corresponding it? It is phi 1. You project the given vector onto this phi 1 and take the modulus square. Okay, that would give you the probability. Okay. And what's that projection? If you project it onto phi 1, you see that phi 1 with phi 1 is 1, phi 1 with phi 2 is 0, phi 1 with phi 3 is 0, phi 1 with phi 4 is 0. It's an orthonormal set. Okay, so what you get is root 2 by root 7 square, right? So root 2 by root 7 square, so that's equal to 2 by 7. So 2 by 7 is the probability that you will measure an energy value epsilon 0, right? In the same way, you can calculate the other things. 3 by 7, you just take C2 modulus of C2 square, modulus of C3 square, modulus of C4 square, okay, and you get the probabilities. These are the possible measured values of energy. Okay, what's the second part of the question? There's another observable now, another operator A cap. All right, consider an operator A cap whose action on phi n is defined by. Right, so we see that these phi n are also eigenvectors of the operator A. All right, these phi n are also eigenvectors of operator A. All right, the eigenvalues are different. You see that A phi n is equal to n plus 1 A 0 phi n. All right, there's another operator, right, of which also phi 1, phi 2, phi 3, phi 4 are eigenvectors, and the eigenvalue equation is given like this: A phi n is equal to n plus 1 A 0 phi n. If A is measured, what values will be obtained and with what probabilities? Okay, again, that's not a very difficult thing. You know that the measured values will be the eigenvalues, so you just do this. If for phi 1 n equal to 1, so it is 2 A 0, comma. For phi 2 you will have what do you say, 2 plus 1, 3 A 0, okay, and 4 A 0, 5 A 0. These are the values that will be measured. I think I didn't make any mistake here. This n here, all right, it's this 1. Now the eigenvalue has nothing to do with this expansion coefficients. All right, some books make this mistake. These are not eigenvalues. These are not eigenvalues. These are expansion coefficients which are normalized to 1. Okay. I have seen some textbooks or some problem books making this mistake of considering these as eigenvalues, but that's wrong. All right, so beware of it. So when you calculate the eigenvalues, you don't have to worry about this expansion coefficients. No, you just look at the state and what is the eigenvalue. So here the eigenvalue is given by n plus 1 A 0. Right. So for n equal to 1, you will have 2 A 0, 3 A 0, 4 A 0 and 5 A 0. These are the possible measured values of A. And with what probabilities? Again, the probabilities are exactly the same as before. Okay. It will be 2 by 7, 3 by 7. Right. Again, it would also be the same. P of, let's say, A1 or probability of measuring 2 A 0. This also equal to probability of measuring a value 2 A 0 for the observable A, okay, etc. It's exactly the same. This is also equal to probability of 5 A 0, okay. Now there is another part of the question which is more interesting, right, which actually makes us use the postulates that we studied, right, that we are familiar with. Suppose that a measurement of the energy yields for epsilon 0, right? Suppose that a measurement of energy yields for epsilon 0. If we measure A immediately afterwards, what value will be obtained, right? So now this question is more important, right? They say that an energy measurement is already made and you got for epsilon 0, right? You measured for epsilon 0, okay? Now after making this measurement, all right, on the measured system, you measure A immediately, right? What value will be obtained and with what probability? And with what probability? And with what probability? All right. So we know that if you measure for epsilon 0, okay, if you measure for epsilon 0 energy, that means that after the measurement, the system has changed to a state corresponding to the eigenvector for epsilon 0 for the operator H cap. All right. And what's that eigenvector? For epsilon 0 corresponded to Okay, for epsilon 0 corresponded to phi 2. Okay, so if the measured energy is for epsilon 0, right, so it's here. For epsilon 0 energy corresponds to the state phi 2, right, or phi 2 is the state with the eigenvalue for epsilon 0. Okay, all right. So that means that after the measurement, the state of the system, once you measure for epsilon 0, it means that the state has reduced to the state phi 2 after measurement. Now the system is in the state denoted by phi 2. Right. Now you are measuring A immediately afterwards on the same system. Right. Now the system, the new state is phi 2. Now if you measure A, what would you get? You would get the corresponding eigenvalue of A. We know that phi 2 is also an eigenvector of A. No, it's also an eigenvector of A with the eigenvalue 3A0. Okay, with the eigenvalue 3A0. Okay. So if you make a measurement energy and you get 4 epsilon 0 and then you measure A, you will get 3A0 with probability 1. With probability 1, because after the measurement of energy, the system is now in the state phi 2, which is an eigenvector of the operator A. Okay, so the probability will be 1. All right. Okay. Now I hope these two problems have somewhat clarified some of the things that we discussed in the postulates. Okay. Now we'll, in order to wind up, in the beginning I had said that there is matrix and wave mechanics. Okay, we have got matrix mechanics due to Heisenberg and wave mechanics due to Schrodinger, and some people are interested in this. So I'll just give a note on it. All right. The theory of quantum mechanics deals in essence with solving this eigenvalue problem. Okay, what are the possible energies of the system? Right, this is an eigenvalue equation. What are the possible energies of the system? So we are worried about finding the eigenvectors corresponding to this and the eigenvalues corresponding to this. All right. Now this equation is quite general and these are abstract. This is quite abstract. What are these operators? All right. We cannot really deal with the equation in this form. All right. We cannot really work with this equation in this form. So what we need to do is that we need to go to some basis. All right. Represent it. So to solve it, we need to represent it in a given basis system. Right? So we need to choose a basis and then you can write this equation in a different manner, which you can actually solve. Right? Now there are two kinds of bases that you can use. You can use a discrete basis. Right? Discrete basis means the eigenvalues are not continuous. Right? Just like phi 1, phi 2, phi 3, etc. Or you could use a continuous basis. Right? The eigenvalues are continuous. For example, position. Eigenvalues are continuous because every possible value for x is a possible position. All right, that's continuous. Okay, so if you use it in discrete, if you use a discrete basis, then we have got matrix mechanics, right? Okay, so the representation of quantum mechanics in a discrete basis yields a matrix eigenvalue problem. Right, it's easy to see that because if you look at this equation, H. What we had is H psi is equal to E psi. Okay, this is the equation we need to solve. As I said, we can always project it to some state phi n. Okay, phi n, or let me say phi j. Phi n, all right, phi n is fine. Okay, H cap psi, you are just projecting it to E phi n psi. All right, fine. Now again, this operator, we don't know what did we have here, right? We don't know how to do this operator, right? What to do with this operator? Again, it's an operator. The other things have become numbers. This is a number, right? This is fine. The right hand side has become a number, right? We don't know what to do with this operator. So what we do is that we introduce a 1 here, all right? We multiply with 1. This is the thing that we always do in physics. You either multiply with a 1 or you add a 0, all right? The thing doesn't change. So we'll do that here, okay? So we have got phi n h cap. Okay, and we introduce the identity operator in terms of the completeness relation. All right, so I'll write it as summation over m phi m phi m. Right? We said this is equal to, the sum is equal to the identity operator, or we sometimes call it simply as 1, and this is known as the completeness relation. All right, so we'll use the completeness relation in here, and you have got psi here. All right, this is equal to, right hand side you don't have to do anything because it's already a number. All right, it's a set of numbers. All right, now what is this? There is you know that you can take the summation outside, summation over m. Okay, phi n h cap phi m, right? Now this has become a number, right? Phi n h cap phi m, this has become, I have just combined these things, so this has become a number, and you have got also another number here, phi m psi, alright, this is equal to E phi n psi, alright. Now what does this become? Alright, I'll write it here, okay. Now this means this phi n h cap phi m, it's a number, we can write it using 2 index h n m. So this is summation over m h n m, right, and you have got phi m psi is equal to E phi n psi, right. Now this phi m psi, we know that it's a component of psi along the direction phi m. We can write it simply as Cm, right, is equal to, similarly this we can write as Cn, because we know that phi m psi is the expansion coefficient. Now what is this? You see that this is a matrix equation. This is an equation for matrix multiplication. You are summing over m, okay, so that means there is not just one Cm, there is C1, C2, C3, etc. And the corresponding matrix equation, this is in the component form. The corresponding matrix equation, you can write it as, there is a square matrix, n by n square matrix, and there is a column matrix, okay, with C1, C2, etc. up to Cn, okay, that's equal to some constant multiplied by a column matrix. Okay, what is this? This is nothing but an eigenvalue equation in the form of a matrix equation, right? Now this equation, we know that once you have an eigenvalue equation in the case of a matrix, we know how to find the eigenvalues, right? So you might have studied A is equal to lambda, right? A lambda is equal to how do we write it? Ax equal to lambda x, and then how do we find the eigenvalues lambda? We know how to do that, all right? We construct this determinant and put it equal to 0, solve it, you get the eigenvalues. Alright, this is matrix mechanics. Okay? And matrix mechanics is the most convenient if the basis used is discrete. Okay, but if you are doing with continuous indices, it's difficult, because then this matrix becomes infinite dimensional. Alright, this matrix becomes infinite dimensional. It becomes difficult. Alright, you could, in principle, you could do this thing. Right, you could actually use it also for discrete basis. I think Heisenberg had struggled with these kinds of equations for a long time without even knowing about matrices. All right, even though matrices were developed at that time, Heisenberg was not aware of them. So he was actually struggling with these kinds of equations, okay, without any knowledge of matrices. All right. So when it becomes infinite dimensions, it's more convenient. All right, if you are using a continuous basis, all right, it's more convenient to use a different kind of representation. All right, it's convenient to use functions and differential operators. All right, so representing the formalism of quantum mechanics in a continuous basis yields an eigenvalue problem in the form of a differential equation. All right, continuous basis means, for example, coordinate base. We are specifically talking about position basis. All right, position basis, which means you are now expanding your state in terms of position eigenvectors. All right, so the expansion coefficient, these are the expansion coefficient. Okay, because x is continuous, instead of a summation we have an integration here. These are the expansion coefficient. Now in principle you could write all these numbers in an infinite column matrix, right? Corresponding to every x you have a complex number, corresponding to every x, every point in space you have a complex number. You could in principle write all these infinite numbers here. All right, you could think, you can imagine, it's the same thing. But it is convenient to write it as a function, psi of x. Right? Psi of x is also a set of complex numbers, just like C1, C2, C3 here, except that corresponding to every point in space you have a complex number. Right? And again, we know that this probability interpretation that we talked about in the case of discrete, we said that if psi is equal to summation n Cn phi n, okay, then the probability of finding the state or measuring an eigenvalue corresponding to an eigenvector phi n would be modulus of, or phi I would be modulus of C I square. Okay. Here also we have that interpretation, because this is the position basis. Right. The modulus psi of x square would be probability, would be associated with, okay, associated with probability of finding particle at x. right? Modulus psi of x square would be associated with the probability of finding the particle at x, right? Now there is a bit subtle. When we discussed double slit experiment, we actually decided to overlook the subtleties introduced by the fact that position is actually continuous, all right? So we just wanted to motivate it. That was the easiest example, right? But since this is continuous, we cannot really talk about one point, one position, all right? Because suppose there are infinite number of positions, right? Suppose there are infinite positions. We know that there are infinite positions because space is continuous. There are infinite number of points in the space. Okay. Now, if you want to find the probability at any one point, all right, any one given particular point, we know that because there is infinite positions, the probability would be 1 by infinity and would be 0, right? So since there are infinite number of possible positions, yes, because position is continuous, the probability, we cannot really talk about finding the particle in an exact spot. Okay, we can only talk about finding the particle in an interval dx, all right? So number of intervals is finite, right? So in an interval dx, so this is the probability of finding the particle in an interval dx, or between x and x plus dx, right? So psi of x, modulus of psi of x square alone, we call it as the probability density, all right? And if this is one dimension, if it's 3 dimension, you will have d cube r vector. Okay, all right, so that's how we do it. And once you represent it in the continuous basis, okay, you get an equation like this, right? The eigenvalue equation, it's the same eigenvalue equation represented in different manners. This is in some discrete basis and this one is in some continuous basis. So this is the operator now. This is known as the momentum operator, square of the momentum operator. All right, not exactly. This is also divided by this factor. This is the energy, the kinetic energy of a free particle operator, for example. Okay. Now the mathematics, in order to deal with the mathematics of continuous basis, you may have to learn a little bit. You might have to get familiarized with a little bit more some of the tricks, all right, because they are continuous. All right. For example, the condition of orthonormality. In the case of discrete, it was simply phi m with phi n is equal to delta nm. All right. We can construct a similar orthonormality relation in the case of continuous eigenvectors also. So, for example, if you have something like x and x prime, all right, this is equal to delta of x minus x prime. This is known as the Dirac delta. Or in general, you can say that if you have some continuous variable k prime, all right, this is equal to delta k minus k prime. All right, this is in one dimension. If it's in 3 dimension, you will have to make the corresponding generalization. All right. Now you see that this delta n, even though they look similar, there are a lot of similarities, but this is 1, all right, at some point. When n equal to m, this is equal to 1, but when x equal to x prime, this is equal to infinity. So we have to be more careful when we deal with the continuous eigenvectors or continuous basis like position or momentum. Okay. Now these are just examples of some of the operators. Okay, we can actually find what these operators are, starting with some assumption like momentum generates translations in time or translations in space, something like that. All right. We don't go into the details. These are some of the mathematical details that you still need to learn, right? Which is beyond the scope of these 5 lectures. Right? So if you have a position, the operator corresponding to position is simply the position itself. Right? So the multiplying by an operator means multiplying by x. That's all. So any function of position, the corresponding operator is the corresponding function, no problem. Right? So the operator corresponding to a potential v of x is simply v of x. And the momentum, x component of momentum, it's h cross by I dou by dou x. Right? And if it is in 3 dimensions, you will have to write as h cross by I in 3 dimensions. The vector operator, you will have this thing here. All right? And Hamiltonian, in the case of time independent, is p square by 2m. This we know that p square by 2m is the usual expression for kinetic energy. All right? It's so p square by 2m plus v of x. E is the Hamiltonian, time dependent. If it's time dependent, we'll also write it like this. Right? Kinetic energy, okay, that's p square by 2m. and z component of angular momentum. These are just some examples of differential operators. So in Schrodinger picture, or in wave mechanics, okay, in wave mechanics, the operators are differential operators and the states are represented by complex functions. Okay. In matrix mechanics, operators are represented by matrices and states are represented by column matrices. Okay. Now, do we have time? I think we'll just talk about this. Now, so far, right, you might have wondered, so if you study quantum mechanics, usually we start with wave particle duality. Right? Usually we start with what we call as wave particle duality. Okay. I don't know if any one of you was surprised. Throughout this lecture, I never mentioned the word wave. Okay. I never mentioned the name wave or the term wave. I never talked about wave. Okay. Even in the double slit experiment, I said that the electron is in both slits at the same time. Okay. I didn't say that electron is a wave or anything. Okay. Now, to think of electron as a wave is slightly problematic, right? Because it's true that there is some sort of wave going on there, but it's not a physical wave, right? What we measure always is a particle. Okay. So on the screen you always find a spot. When you find a particle, you always find one particle, right? So when you measure, the electron is always a particle. Okay. So one way to look at it is, we have quantum mechanics as a logical framework, right? We can do the quantum mechanics of particles, we could do the quantum mechanics of waves or anything, right? So the way I have described it here, it's the quantum mechanics of particles, right? I have assumed that electrons are some sort of particles with definite positions when you measure them, all right? So these are particles, and we use the rules of quantum mechanics, including the principle of superposition, right? So instead of using the terminology of wave, I just assumed that just as the mathematics describes, the particle is actually in different places at the same time. Okay. So the state of the particle, right? It's here, it's everywhere. All right, it's everywhere at the same time. I didn't have a wave thing. Right? But why do we have this wave particle duality kind of thing? I'll just explain it. Okay. If you take the momentum eigenvector and find the representation in coordinate basis. All right, this is what you will get. This is the momentum operator in position basis. Momentum eigenfunction position basis. Right? You can easily check this. You can see that this is an eigen function of the momentum operator. Right? H cross by I, dou by dou x acting on, dou by dou x acting on, this is the normalization factor, you can leave it, acting on e raised to I px by h cross. All right. Okay. So you see that the momentum operator acting on this state gives you see that it's d by dx, so this p will come out. Okay, h cross and h cross, I and I will cancel. This is equal to p multiplied by e raised to I px by h cross. Okay, you see that the momentum operator acting on this function gives you momentum multiplied by the same function. So this is an eigen function of the momentum. Alright. So eigenfunction, by eigenfunction we mean wave functions representing eigenvectors, alright, or eigenvectors in coordinate basis. That's what we mean by eigenfunction. Okay. And so what we did now is we checked that this is actually an eigenfunction of the momentum so this is an eigenfunction corresponding to the momentum eigenvector. Right? In other words, this is the representation of momentum eigenvector in the coordinate basis. Right. Now, if you look at this, you see that this looks like a wave. All right. But we know that what are these actually? What do we get here? These are expansion coefficients. Expansion coefficients. This means that if you want to expand the momentum eigenfunction, okay, if you want to expand the momentum eigenvector in terms of the coordinate basis, all right, what you do is that you integrate this equal to, we will have some psi p of x, I will write it, okay, x dx, all right, and this expansion coefficient, these are these expansion coefficients, and this expansion coefficients is this thing, right. We represent the vectors or functions of vectors by their expansion coefficients in a particular basis. Right. So these are basically the expansion coefficients, which by taking the square, by taking the complex, by taking the modulus square, you can find the probabilities. Okay. Now if you look at this thing, all right, this is also known as a free particle. free particle momentum eigenstates, right? Free particle solution. This is also a free particle solution. We won't go into the details there. But if you look at this momentum eigenvector in coordinate representation, you see that this looks like a wave, all right? It has the form of waves. Okay? If you expand this, you get cos px by h cross plus I sin px by h cross, and this is a wave like this, all right? If you draw only the real part, it's a wave like this. It's a plane wave, right? So if you take this function corresponding to every x, you get a complex number, right? If you draw only the real part, you get something like that, all right? A sine wave or a cosine wave, okay? This is only the real part. Of course, there is imaginary part which I cannot draw here. Right. Now, if you look at this, you see that if x varies by a factor 2 pi h cross by p, it remains the same. All right. You see that the displacement in the wave remains the same. Displacement in this function, or the function remains the same if you change x to x plus 2 pi h cross by p. That's how you calculate the wavelength. Right. What's the wavelength? What's the wavelength? If this is the height, right, wavelength, this distance is the wavelength, all right? It's the distance between points at the same phase, distance between the points which are exactly at the same phase. So you see that if you add 2 pi h cross by p to this x, all right, this becomes, you know that this becomes e raised to I px by h cross multiplied by e raised to 2 pi I, all right, and you get back the same thing because this is equal to 1, right? So you see that this thing behaves like a wave with wavelength 2 pi h cross by p, all right? Or if you put h cross equal to h by 2 pi, you will get h divided by p. Now you see that these are the probability amplitudes, okay? These are actually the probability amplitudes. So the wave is not a real wave. It's not in a real wave. It's just that the expansion coefficients, all right? They show a wave-like pattern with a wavelength h by p. Of course, this is important, but it doesn't mean that there is any real physical wave out there, all right? Because if you take a two-particle system, then this wave exists in 6 dimensions. Okay, it's the configuration space. If it's a one-particle system, the wave exists in 3 dimensions. It's fine. But if you take a two-particle system, again you can construct a wave like this, but then that will exist in 6 dimensions. Okay, so it's not actually a real wave. It's not any real wave that exists in space. So it's not actually entirely right to talk about a wave-particle duality. Not in this framework, all right? Here we have assumed, the way I have described, we have assumed that electrons are particles, and we have used the quantum rules or the quantum framework to describe particles called electrons, all right? This is one way of looking at it, all right? Now, you can think of this expansion coefficient psi of x and say that, all right, this looks like a wave, this wave is spread out like this, so you can call it as a wave, but you have to remember that this is not in a real physical wave. These are just probability amplitudes showing a wave-like pattern, okay? So if you just plot the probability, because corresponding to every point you have the probability, it is like this. These are just a set of probabilities or probability amplitudes to be precise, okay? So it's not absolutely necessary that you think of a wave-particle duality. You don't have to think of electron as a wave, right? At least this framework does not force us to do that. I think it's more simple, it's more consistent to think of electron as a particle, and this framework is the quantum mechanics of particles. Now you can think of electron as a field, and then you will have to do a quantum mechanics of field, and we have the quantum mechanics of field. It's known as quantum field theory. Okay, but once you go to relativity, you see that considering electron as a particle is not entirely correct. You need to consider electron as a field. Yeah? You assume that electron is a field that's spread throughout all space, and then you can use the same quantum mechanical rule, the same quantum mechanical logic to describe fields, and then you will have a different theory called quantum field theory, right? But in this non-relativistic quantum mechanics, it's fine to think of electrons as particles, right? We are doing quantum mechanics of particles, and in this framework, particles just exist in different points at the same time, or different states at the same time. You don't have to talk about waves at all, okay? But this relation is important, right? This relation is important. It has also physical importance, because this relation tells us about how the probabilities of finding the free electron in space are distributed, all right? This relation, actually, this wave-particle duality thing, or it's normally called the de Broglie wavelength, okay? De Broglie wavelength. Okay. So the de Broglie wave actually tells us that it's important that the probability amplitudes are distributed in this form. All right, it has experimental consequences, but it's not a real wave. All right, it's not a real wave. There is no wave. There is only particle. At least in this formalism, in the way I have described. Of course, we can think about wave-particle duality also, but I think it's a bit confusing. You don't have to think about it as a wave. Okay. Now comes the million-dollar question: what does it all mean? All right, we said, all right, we have formalized quantum mechanics into a set of postulates. We said the mathematical framework, we know how to make predictions, but what does it all mean actually? All right, to say that electron is in two places at same time. Right? Now, even Schrodinger came up with the wave mechanics, Schrodinger equation. But even Schrodinger's equation predicted that there is some property called superposition, because it's a property of the differential equation. If psi 1 and psi 2 are two solutions, for example, two solutions, then by the property of the differential equation, psi 1 of x plus psi 2 of x is also a solution. All right, this is principle of superposition. And Schrodinger, even though he came up with Schrodinger equation and it made good predictions, he could not believe that there is something called superposition. And maybe he was ready to accept there is superposition, but then he couldn't believe there was something called measurement problem, right, or the collapse of the wave function. Right? So Schrodinger said, all right. So Schrodinger said that, all right, this is all a bit weird. Okay, I am sorry I had anything to do with quantum mechanics. Okay, so this is how he explained to explain the weirdness of quantum mechanics. Okay, he just took a macroscopic example. Right? He said that, right, consider a box which is isolated from the environment, completely isolated from the environment, and put a cat inside of it. Right? You put a cat inside of it, and inside the box, this is perfectly isolated from the environment, and inside the box, what do you have? You have got a beaker of cyanide poison, cyanide gas, right? And on top of the gas is hanging a weight. Right? If the weight falls on this, it will break. Right? And if the box breaks, what happens? The cat dies because it's cyanide gas or poisonous gas. Now, there is an ingenious device in here. Okay? There is just one radioactive atom inside this box. Just one radioactive atom. Radioactive atom. There is just one single radioactive atom inside this box. And the decay of a radioactive atom is a quantum mechanical phenomenon. Right? It's quantum mechanical, it's random. That's why we talk about average lifetime or half-life, etc. So if you take a single radioactive atom, you don't know, it's not determined in that sense whether it will decay now or it will decay after some time or after later time. Right? We can only talk about average lifetime. If you take one single atom, you don't know when it will decay. Quantum mechanics says that you don't know when it actually decays. Right? So if this non-decayed atom is in the box, right? Quantum mechanics says that after some time, right, what's the state of this atom? What's the state of this atom? Okay. So we know from the principle of superposition that the state of the system is a superposition of all possible states, right? What are the possible states? It could have decayed and it could be not decayed. Right? So the state of the atom, I will write it like this. State of the atom after some time, it's possible that it has decayed, it's possible that it has not decayed, right? So the general state is a superposition of both these states, right? So let's wait exactly until time so that this coefficient becomes 1 by root 2. Now quantum mechanics does not say that it's either decayed or not decayed. Quantum mechanics, the way we chose to speak about it, quantum mechanics is saying that it's both decayed and not decayed at the same time. That's superposition for you. Right? It has to be in both slits at the same time. Right? But what's the corresponding state of the cat? What's the corresponding state of the cat? If the atom is decayed, the cat is dead. Right? If the atom is decayed, the cat is dead. If the atom is not decayed, the cat is alive. So state of the cat is dead plus alive. Right? So Schrodinger is asking, right? So are you saying that the cat is both dead and alive at the same time if you are not looking at it? Okay, that's quite a sad story for the cat. Okay, so quantum mechanics in this situation, if you take it literally, all right, if you take quantum mechanics literally, it says that the cat actually is dead and alive at the same time inside the box, right? But once you open, you never see the cat in superposition, right? So let's say we had a happy ending to our experiment, okay, and Yeah, Schrodinger's it's maybe Schrodinger did not like cats, all right, to put cat into such a position. But the thing is that when you open the box, you see either a dead cat or an alive cat. You never see the cat in superposition, right? So this is what, suppose I opened the box and I saw a cat which is alive. The state of the cat has changed from this to this, right? This is wave function collapse for you. Okay? Now Schrodinger is asking, can you believe this? Right? It's so weird. Can you believe this? Right? Now this is a real problem, all right? Because we don't know how the wave function collapses or why the wave function collapses. All right. Now the mathematics of quantum mechanics as such does not predict that wave function has to collapse. The mathematics of quantum mechanics only says that the wave function or the state vector evolves according to the Schrodinger equation, and in that evolution, it's a smooth evolution, there is no collapse. All right. Collapse is an extra postulate that we have to give in order to make sense of the experimental observations. All right. The fact that we always see the electron only in one of the slits, for example. So this is known as also the measurement problem, and it's still an open problem. All right, there is no consensus as to what happens during the measurement. All right, so if you take quantum mechanics literally, it says something actually. All right, maybe we don't have time. Let's see if we can. All right, so there are many interpretations of what the mathematics of quantum mechanics means. We all know that the mathematics of quantum mechanics works. Okay? There are different interpretations as to what it actually means about an electron. There is one thing called Copenhagen interpretation. Okay? This is the what you say, the orthodox interpretation. Orthodox interpretation. Orthodox interpretation. All right. So in this orthodox, this was actually put together by people like Bohr and Heisenberg. Okay, they just got together. Max Born, they just got together and decided, all right, this is the solution to the problem, because they thought it unproductive to think about these questions. All right. So the basic idea of Copenhagen interpretation is that the mathematics, the quantum mechanics is just a mathematical way to calculate probabilities, and it doesn't actually really mean anything. It doesn't really tell us anything about the actual way electrons behaves in the nature. It's just a tool to calculate probabilities, right? Because we cannot measure an electron in superposition, etc. There's no point in considering it as a literal thing. That's what they said. According to them, it's just a tool to calculate probabilities. It doesn't tell us what actually happens in nature. Okay. There's also one interpretation called many worlds interpretation, which takes quantum mechanics literally. Now, in Copenhagen interpretation, when I say that the state is summation of I, Ci, phi I, it doesn't mean that it's actually in different states at the same time, all right, in this interpretation, all right. But there is a literal interpretation which says that this is actually the state of the electron. The electron is actually in different places at the same time, all right. There are different literal interpretations. One of the approaches taking the wave function literally or taking quantum mechanics literally is known as the many worlds interpretation, all right. So in the many worlds interpretation, what happens is this. Okay, so when I showed the state of the cat, I was actually cheating a little bit. The actual state of the cat is given like this, all right, because cat alone does not have a definite state. All right, what we have is an entangled system of the particle and cat. Right? Once the particle and the cat or the box has interacted, we don't have separate wave functions. We don't have separate states for the system. What we have is an entangled state. That's what quantum mechanics predicts. All right. So after the atom has decayed, we don't have separate wave functions for the cat and the atom. All right. We only have a combined wave function. All right. On one branch of the wave function, we have an atom which is not decayed, and in that branch, the cat is alive, and on the another branch, the atom is decayed, and in that branch the cat is dead. All right. So isolated system, for isolated system we can consider separate wave function, but once the system is not isolated, you only have a wave function for a combined system. Okay. That's what quantum mechanics predicts. All right. Now what happens? Now if you measure an alive cat, what actually happens is that you are finding yourself in this branch of the wave function. Well, this I'll call generally as the wave function. Alright, I'll generally call it as the wave function. So the wave function actually collapses to this state. Alright. Okay. Now, if you assume that the wave function is not actually collapsing, alright, if you assume that the wave function is not actually collapsing, what happens is that the atom not only interacts with the cat, but the cat interacts with the environment. Right? So it gets entangled with the environment. Okay. Now once you open the box, it gets entangled with you. Alright, it entangled with you looking at it. Right. So the environment of the dead cat is different from the environment of an alive cat, because a dead cat is lying down, and correspondingly the positions of other particles will have changed, or the states of the other particles will have changed, etc. Alright. So if you take quantum mechanics literally, this is the state of the quantum mechanical system after it reacts with the environment, and then environment immediately reacts with you and the rest of the universe. Right. So in this interpretation, the many worlds interpretation is saying that the universe actually separates into two branches, because the environment is interacting with the rest of the universe. The wave function does not collapse. The wave function actually does not collapse, but the universe actually branches into these two branches. Both these branches exist. Alright, and both these branches, in one of the branch you will have measured, you would have seen an alive cat, and in the other branch you would have seen a dead cat. Alright, so by each measurement, each measurement of a quantum mechanical phenomenon, the universe is actually splitting into branches. Alright, so according to this interpretation of quantum mechanics, the many worlds interpretation, according to many worlds interpretation, there are possibly infinite versions of you existing, because when each quantum event occurs, the universe is actually splitting into separate branches. All right. So in this picture, the whole universe has just one wave function, and this evolves according to Schrodinger equation. You don't have to introduce anything like wave function collapse. There's only an appearance of wave function collapse. What happens is that you become part of that wave function. All right. You become part of the wave function. There is one in which you see the cat alive, okay, and you are happy. All right. And there is another universe in which you see the dead cat, and then you are sad. Right? So this would be the total state of the universe, including you. This is the many worlds interpretation, and there are people who take this really seriously. All right, because without bringing any extra thing like measurement problem or extra thing like wave function collapse, you believe that quantum mechanics is correct and ask, what does it tell us about the universe? And this is what quantum mechanics tells you about the universe. All right? There are problems in this interpretation also, but especially when we start to study the whole universe using quantum mechanics, you may have to consider a wave function for the whole universe. There is a branch called quantum cosmology, and in that, people who work in that, many physicists find this as the better interpretation. All right, but again, there is no consensus. We don't know what's actually happening.